On a clear night in the southern skies, low over the horizon, there is a bright point of light that most people walk past without a second thought. It looks like a single star. It is really 3 stars bound together, and it is the closest star system to our own, a place called Alpha Centauri. For as long as we have known what stars are, this has been the nearest shore across the dark, the first place we might one day sail to. And so, a quiet question follows on its own. If we ever sent people there, what would the journey actually ask of them? Anyone who crosses that distance and arrives at Alpha Centauri will almost certainly never come home again, and the reason is not danger or accident, but distance, time, and the plain arithmetic of the trip itself. Tonight, slowly and gently, we will walk through all of it together. Go outside on a clear night in the southern half of the world and look low toward the horizon, into the constellation we call Centaurus. There is a bright point of light there, steady and warm, one of the brightest in the whole sky. To your eye, it is a single star. People have watched it for thousands of years and thought the very same thing. It sits close to the Southern Cross, and travellers once used that patch of sky to find their bearings. From the far south of Australia, from Chile, from South Africa, it rides high and is easy to find. For most of the northern world, you never see it at all. It stays hidden below the curve of the Earth, waiting for anyone who travels far enough south to meet it. That single point of light is not one star. It is the blended glow of at least 2 suns, mixed together across a distance so great that your eye cannot pull them apart. Its name is Alpha Centauri. Counted as one point, it is the 3rd brightest star in the whole night sky, after Sirius and Canopus, and of everything you can see up there, this is the closest to home. Closest is a gentle word that hides something enormous. The light landing in your eye tonight left Alpha Centauri more than 4 years ago. It crossed the empty dark the entire time, travelling at the fastest speed anything can travel, and only now has it arrived. You are seeing that place not as it is, but as it was, back when a small child was learning to walk. Back before some season you still remember. Every star works this way. The night sky is a kind of memory, each point showing you the past. Alpha Centauri shows you the most recent past of any star there is. For most of human history, that was the end of the story. A bright dot, a name, a fixed place among the constellations. The ancient watchers in Egypt and in the southern deserts knew it as a marker and little more. They had no way to know what it was made of, or how far it sat, or whether anything circled it in the dark. It was simply there, faithful, returning to the same place each year as the Earth swung around the sun. We know a great deal more now. We know the point is a family of stars. We know that at least one small world turns around one of them, a world close enough in size to our own that people wrote its name down and wondered. We know almost exactly how far the light must travel to reach us. And knowing all of that, a quiet thought begins to press forward on its own. If this is the nearest shore across the dark, the very first place we might one day sail to, then what would it take to actually go? Not to look, to leave here and arrive there. That single question opens onto a much larger one, and it is the one we will follow tonight slowly, all the way down. Because when you work through the distance and the time and the plain arithmetic of the trip, you arrive at something strange and steady and true. Anyone who ever crosses that gap and reaches Alpha Centauri will almost certainly never come home, not for lack of courage, for reasons built into the shape of the universe itself. We begin with the light and we follow it out. Look again at that point of light and imagine drawing closer, close enough to finally separate what your eye blends into one. What comes apart is a small family of stars, 3 of them, bound together by gravity into a single system. The first is Alpha Centauri A. It is a star remarkably like our own sun. It is a little larger, a little brighter, and it burns the same steady yellow-white. If you set our sun beside it, you would struggle to tell them apart. It is close enough to the sun in mass and temperature that scientists often call it a solar twin, and it is the brightest of the 3 by a clear margin. Most of the light you see with your eye comes from this one star. The second is Alpha Centauri B. It is smaller and cooler, an orange star with a little less than the mass of our Sun. It burns gentler and dimmer, the colour of a warm lamp rather than midday. These two, A and B, are true companions. They circle each other slowly, held close by their shared gravity, completing one orbit about every 80 years. Over a human lifetime, you could watch them swing all the way around one another. At their nearest, they come about as close as our Sun is to the planet Saturn. At their farthest, they drift out to roughly the distance of Pluto. They dance patiently on a track that takes a lifetime to trace. The third member is the quiet one, and it changes the whole story. Its name is Proxima Centauri. It is a red dwarf, a small, cool, deeply faint star with only about 1/8 the mass of our Sun. It is so dim that no human eye has ever seen it without a telescope, even though it sits among the nearest stars in existence. It was found in the year 1915 by the Scottish astronomer Robert Innes, working from an observatory in South Africa. He noticed a faint red star that seemed to share the motion of the brighter pair, drifting across the sky alongside them. Proxima does not hug its companions the way A and B hug each other. It floats far out, more than 10,000 times the distance between the Earth and the Sun, off at the ragged edge of the system. It is so far from the central pair that a single loop around them may take it more than 500,000 years. For a long time, no one was even certain it belonged to the family at all. It might have been a stranger passing through. Careful measurements have since shown that it is very likely bound, held in that vast, slow orbit, a distant cousin to the two bright suns at the centre. So the point of light is 3 suns, one much like ours, one a smaller orange companion, and one dim red ember drifting far out in the cold. Together they make the closest star system to Earth. And here the story turns in a way that matters for everything to come. The star at the centre, the bright familiar one, is not the nearest of the 3. That title belongs to the quiet red ember on the edge. Proxima Centauri, the faintest of the family, the one you cannot see at all, happens to sit closer to us than any other star in the sky. It is the true nearest neighbour, and it is where we go next. Of all the stars in the night, one sits closer to the Sun than any other, and it is Proxima Centauri. The name itself carries the fact plainly. Proxima comes from the Latin word for nearest. When Robert Innes found that faint red star drifting alongside the bright pair, and later measurements showed how close it sat, the name almost chose itself. It is the nearest star to our own, and it will hold that title for tens of thousands of years to come. How near is near? Proxima Centauri lies about 4¼ light-years away. A light-year is the distance light covers in a single year, moving at 300,000 kilometers every second, without pause, for 365 days. That distance comes to nearly 10 trillion kilometers. Proxima sits a little more than 4 of those lengths out. Written in kilometers, the number sags under its own weight, something close to 40 trillion. The mind slides off a number that size. We will find better ways to feel it soon. For now, hold the small, strange fact at the centre of it. The closest star to Earth, our nearest companion in all the heavens, is a star you cannot see. Proxima Centauri glows so faintly that without a telescope it stays completely hidden. It gives off less than 1 part in 1,000 of the light our Sun pours out. If you swapped our Sun for Proxima, high noon would look like a deep, dim dusk. It is a small, slow-burning star, the most common kind in the galaxy by far, and it will keep burning steadily for trillions of years, far longer than the Sun ever could. The 2 bright stars beside it, Alpha Centauri A and B, sit just slightly farther, about 4⅓ light-years out. So when we speak of travelling to Alpha Centauri, we're really speaking of a small neighbourhood, 3 stars clustered together at nearly the same enormous distance. Reach one, and you have essentially reached them all. Proxima, being nearest and holding a world we will meet shortly, is usually the one people picture at the end of the journey. It helps to know how we measure a thing so far away. Astronomers use an old and elegant trick called parallax. Hold up one finger at arm's length and look at it with one eye, then the other, and it appears to jump against the background. The jump comes from your two eyes seeing from slightly different places. The Earth does the same as it orbits the Sun. In summer, we sit on one side of that orbit. Half a year later, we sit on the far side, hundreds of millions of kilometers away. A nearby star, watched from those two vantage points, shifts by a tiny amount against the distant stars behind it. Measure that shift and simple geometry hands you the distance. Proxima's shift is small, a fraction of the width of a human hair held far from your face, but our instruments can catch it cleanly. So we know, with real confidence, that a star sits 4¼ light years from here, faint and red and patient. It is the doorstep of the wider galaxy, the first light beyond our own sun. And in the year 2016, watching that faint red star with great care, astronomers found something turning around it. A world. That is where the pull toward Proxima truly begins. In the year 2016, a team of astronomers announced that they had found a planet circling Proxima Centauri. They named it Proxima b. It was the nearest planet ever discovered outside our own solar system, orbiting the nearest star there is. For anyone dreaming of a journey to another sun, it was the closest thing to a destination that reality had ever offered. They did not see the planet directly. Proxima is faint, but next to a planet it is still blindingly bright, and the world is lost in the glare. Instead, the team watched the star itself for the smallest possible motion. A planet does not simply orbit its star. The two pull on each other, and the star wobbles a little in place, tugged by the gravity of the world going around it. That wobble shifts the colour of the star's light by a hair, toward the blue as it moves toward us, toward the red as it moves away. The effect is tiny, a change in speed of only a metre or two each second, a walking pace measured across 4¼ light years. Catching it took years of patience. The instrument that caught it has a plain name, HARPS, a spectrograph mounted on a telescope at the La Silla Observatory, high in the dry mountains of Chile. The campaign that clinched the discovery was called Pale Red Dot, led by the astronomer Guillem Anglada Escudé. Night after night they measured the colour of Proxima's light, watching for the faint rhythm of a tug that repeated on a steady beat. The beat was there. Every 11 days or so the star wobbled the same small amount. Something roughly the mass of the Earth was swinging around it. Here is what set hearts racing. Proxima b sits in what astronomers call the habitable zone. That is the band of distances around a star where the warmth is right for liquid water to sit on a surface, neither boiled away nor frozen solid. Water, so far as we know, is the one thing life cannot do without. Because Proxima is so faint and cool, that warm band lies very close in, far closer than Mercury sits to our Sun. Proxima b hugs its star tightly, completing a full year in the time it takes the Earth to spin around 11 times. Yet because the star is so dim, that tight orbit receives roughly the gentle warmth that could allow water to pool. A world the size of ours, at the right temperature for oceans, around the nearest star. It reads almost like an invitation. The honest picture is more tangled, and worth saying plainly. We do not know if Proxima b holds water or air or anything at all. Red dwarf stars like Proxima are prone to violent flares, sudden bursts of radiation far stronger than anything our steady sun throws off. And those flares could strip a nearby planet's atmosphere away over time. The planet very likely keeps one face turned always toward its star, the way the moon keeps one face toward Earth, leaving one side in permanent day and the other in permanent night. Whether a world like that could hold on to air and water is a question no one can yet answer. We know its mass, roughly, and its orbit, and almost nothing else for certain. Still, it is there, real and near, and the right size, turning slowly around a faint red star just over 4 light years away. And a planet you can name is a planet you can dream of reaching. So the old question sharpens into something specific. How far really is 4¼ light years? That is what we feel next. 4¼ light years. We have said the number, but a number that size means nothing until you can feel it in the body. So let us make it something a person can actually hold. Start with light itself, the fastest thing there is. Light crosses the space between the Earth and the Moon in a little over 1 second. It travels from the Sun to your face in about 8 minutes, which means the sunlight warming you left the Sun before you stepped outside. It reaches Jupiter in most of an hour and crawls all the way out to the edge of our solar system, past Pluto, over the course of several hours. Nothing moves faster, and even light, the swiftest thing in the universe, needs more than 4 years to reach Proxima Centauri. 4 years of unbroken travel at the ultimate speed, just to arrive. Now slow down to something human. Picture a jet airliner cruising at 900 kilometers an hour, the kind of flight that crosses an ocean in a single restless night. Point that airliner at Proxima Centauri and never let it stop. It would fly for about 5 million years before it arrived. The whole span of human history, every city ever built, every language ever spoken, fits many times over inside that flight. Our species is only a few 100,000 years old. The airliner would need to fly for far longer than humans have existed. Try scaling the whole solar system down to something you can see on a table. Shrink the Sun to the size of a small orange sitting in front of you. On that scale, the Earth becomes a grain of sand circling about 10 meters away across a room. Jupiter is a peppercorn out past the walls. Pluto's a speck of dust half a kilometer off at the edge of your town. And Proxima Centauri, the very nearest star, the next orange on the table. On that scale, it sits more than 2,000 kilometers away. You would place your orange-sized sun in one country and have to carry its nearest neighbour across an entire continent to set it down. Between the two, nothing. Empty table. That emptiness is the truth of space. The stars are not crowded together like lights in a city. They are scattered impossibly thin, with vast dark gulfs between each one. Here is perhaps the gentlest way to feel it. When you look up at Proxima's neighbours and see that bright point of Alpha Centauri, you're looking at our closest possible star, and its light still took over 4 years to arrive. Every other star you can see is farther, most of them far, far farther. Their light decades or centuries or thousands of years old. The nearest is already almost beyond imagining. It is the first step out the door, and the first step is already a gulf that light itself takes years to cross. This is why the journey is so hard, and why everything that follows carries such weight. We are not talking about a long trip in the ordinary sense, the way a voyage across an ocean is long. We are talking about a distance that dwarfs every distance a human being has ever crossed, by a factor so large the mind cannot draw it. The moon, which only a handful of people have ever visited, is right next door by comparison, a step onto the porch. Proxima is the far side of an ocean that has no other side we can reach, and yet we have already thrown small machines out into that dark. They are flying right now, faster than any human being has travelled, carrying a little of us outward. It is worth seeing how far they have come, and how far they still have to go. We have already begun to leave. 2 small spacecraft are out there tonight, flying beyond the edge of our solar system, farther from home than anything human hands have ever sent. Their names are Voyager 1 and Voyager 2, and they have been travelling since the year 1977. They were built for a shorter errand. Their task was to visit the outer planets, to fly close to the great gas worlds and send back the first clear pictures of them. Voyager 2 launched first in August of that year, and Voyager 1 followed a few weeks later on a faster path. Together they gave us our first real look at Jupiter's swirling storms, at the fine detail of Saturn's rings, and Voyager 2 went on alone to sweep past Uranus and Neptune, the only spacecraft ever to visit those 2 distant worlds. They did their job beautifully, and then they simply kept going, because once you are moving that fast through empty space, there is nothing to stop you. Voyager 1 is now the most distant human-made object in existence. It sits more than 20 billion kilometers from the Sun, so far that its radio signal, travelling at the speed of light, takes almost a full day to reach us. It has crossed out of the bubble of particles our sun blows around itself and entered true interstellar space, the medium between the stars. Each carries a golden record, a phonograph disc holding sounds and images of Earth, greetings in dozens of languages, music, the pattern of a heartbeat, in case anything, ever, finds them drifting. Now hold their speed in mind. Voyager 1 is moving at about 17 kilometers every second. That is roughly 60,000 kilometers an hour, far faster than any rocket that carries people, faster than a rifle bullet by a wide margin. At that speed, it crosses the distance from the Earth to the Moon in a few hours. It is genuinely, astonishingly fast by any human measure. Pointed at the nearest stars and the speed collapses into helplessness. To cross the distance to Proxima Centauri, 4.25 light years, Voyager 1 would need something close to 70,000 years. Neither Voyager is actually aimed there, but the number is what matters. 70,000 years. When Voyager 1 has travelled that long, the constellations themselves will have rearranged, because the stars drift slowly across the sky over such spans. The whole of recorded history from the first written word until now covers only about 5,000 years. 14 lengths of all human history would pass before our fastest deep space traveller arrived at the closest star. There is a gentle, humbling image in this. In about 40,000 years, Voyager 1 will drift within a light and a half of a faint star in the constellation of the Giraffe, a red dwarf called Gliese 445. It will not stop, or orbit, or signal. It will simply pass in the dark, its power long dead, a silent metal thing coasting through a system that never knew it was coming. That is the closest either Voyager will come to reaching another star 40,000 years from now, and it is only a distant passing in the night. So we have already thrown ourselves outward, and we have thrown ourselves hard. The Voyagers are triumphs, still whispering back to us across the dark after nearly 50 years, and they show, with quiet finality, that the ships we have are far, far too slow. If 17 kilometers a second buys us 70,000 years, we need to go faster. So we built something faster. We built the fastest thing there has ever been. There is a spacecraft flying right now that has broken every speed record humans have ever set. Nothing built by human hands has ever moved as fast. It is called the Parker Solar Probe, and it launched in the year 2018 on a strange and daring mission to fly closer to the Sun than anything before it, to reach into the Sun's outer atmosphere and touch a star. To do that, it does something clever. It does not simply carry engines powerful enough to reach such speed, because no such engine exists. Instead, it falls. It uses the gravity of the planet Venus, swinging past it again and again, each pass tightening its loop and dropping it closer to the Sun. And as it falls toward the Sun's own immense gravity hauls it faster and faster, the way a stone gathers speed rolling down a long hill. By late in the year 2024, on its closest approach, the Parker Solar Probe was moving at about 190 kilometers every second. Sit with that figure for a moment. 190 kilometers in a single second. That is more than 10 times faster than Voyager. It is fast enough to cross the whole of the United States in under a heartbeat. Fast enough to travel from London to New York in under 30 seconds. At that speed, you could circle the entire Earth in about 3.5 minutes. It is, by an enormous margin, the fastest a human-made object has ever travelled. When we talk about the outer limit of what our engineering can do, this is it. This is the ceiling. Now aim the fastest thing we have ever built at the nearest star, and watch even this collapse. At 190 kilometers a second, held steady the entire way, the Parker Solar Probe would need something like 6,000 or 7,000 years to reach Proxima Centauri. It is far better than Voyager's 70,000, better by a factor of 10, and it is still hopeless for a human being. 6,000 years ago, the first cities were only beginning to rise between the rivers of the ancient world. If our fastest craft had set out for Proxima back then, at that record speed, it would still not have arrived. 200 generations would live and die during the crossing, and there is a catch that makes even this comparison too kind. The Parker Solar Probe only reaches that speed for a brief moment, at the very bottom of its fall toward the Sun, whipped up by solar gravity right beside the fire. It cannot hold that speed. Pull it away from the Sun, and it slows again, because there is nothing out in the dark to keep hauling it forward. Its record is a fleeting thing, borrowed from the Sun for a few hours, not a cruising speed it could carry to another star. A real journey would have to reach such a speed and hold it, through engine power alone, across the entire crossing. Nothing we have built comes close to doing that. So here is where the plane arithmetic has brought us. The fastest object humanity has ever made, at the very peak of its speed, would still take thousands of years to reach the nearest star and cannot even truly hold that speed. The ships we have are not slow by a little, they are slow by a factor of thousands. And knowing all of this, knowing how impossibly far it is and how impossibly slow we are, we still look up at that point of light and dream of going. It is worth asking gently, why? Knowing everything we now know, that the nearest star is 4 light-years off, that our fastest machine would take thousands of years to arrive, a reasonable person might simply let the dream go. And yet we do not. We keep looking up at that faint point of light and imagining ourselves there. It is worth sitting quietly with why that pull is so strong, because it explains why people keep doing the hard arithmetic instead of walking away from it. Part of it is very old. For as long as there have been humans, we have moved toward the horizon. Our ancestors walked out of one small part of Africa and, over tens of thousands of years, spread across every habitable corner of the planet. They crossed deserts on foot, followed coastlines into unknown lands, and pushed small boats out across open ocean toward islands they could not yet see, with no promise of anything on the far side. The people who settled the vast scatter of the Pacific did it in wooden canoes, reading the stars and the swells, sailing into emptiness on the faith that land lay somewhere ahead. That restlessness, that willingness to leave the known behind, is written deep in us. The stars are only the next horizon, the one we have not yet found a boat for. Part of it is the simple wonder of a second shore. For the whole of history, every human being who has ever lived has lived on this one world. Every story, every war, every love, every quiet morning, all of it on a single small planet circling a single ordinary star. Proxima b, whatever it turns out to be, is the first concrete hint that there might be another ground to stand on, another sky to look up into. Even if it proves to be a barren, airless rock, the idea of it changes something. It makes the universe feel less like a wall and more like a door. And part of it is quieter and hard to name. It is the sense that we are, in some way, meant to try. That a species which can measure the wobble of a star 4 light-years away and calculate exactly how far and how fast and how long might also be a species that eventually goes, not for profit, not for escape, but because the reaching is part of what we are. When we sent the Voyagers out with their golden records, we were not being practical. We were saying, to whatever might find them, that we were here, that we looked up, that we wondered. If any part of that pull toward the nearest stars is one you feel as well, consider subscribing, and we can keep following these quiet questions together on nights like this one. None of this makes the distance any shorter. The wonder does not bend the arithmetic. 4 1/4 light-years remains 4 1/4 light-years, whether we long for it or not. But the longing is the reason the calculation gets done at all, the reason serious people have spent whole careers designing ships for a voyage no one alive will take. They do it because the pull is real, and because working out how it might be done, honestly and carefully, is its own kind of reaching. So we turn from why to how. If we truly wanted to send something, or someone, to Alpha Centauri, what would it take? The answer begins with a problem so fundamental that it shapes every rocket that has ever flown, a problem written into the very nature of how rockets move. It is sometimes called the tyranny of the rocket equation, and it is where the real difficulty starts. Every rocket that has ever left the ground fights the same quiet enemy, and it is not gravity, and it is not the cold of space, it is fuel. The problem is so basic that it was written down more than a century ago in the year 1903 by a self-taught Russian schoolteacher named Konstantin Tsiolkovsky, working alone in a small town far from any city. He never built a rocket, he simply worked out, with clear mathematics, how one must behave, and what he found sets the shape of every launch we have made since. A rocket moves by throwing mass out behind it. It burns fuel, flings the hot exhaust backward at high speed, and the push of that thrown mass drives the rocket forward. That is the whole secret. To go faster, you must throw more mass, which means you must carry more fuel. And here the trap closes. The extra fuel has weight of its own. To carry it, you need still more fuel to push that fuel, and that additional fuel also has weight, and needs pushing too. The demand does not grow gently, it grows in a way that runs away from you, climbing faster and faster the more speed you ask for. Tsiolkovsky's equation puts this plainly. To make a rocket go a little faster, you add a bit of fuel. To make it go twice as fast, you do not need twice the fuel. You need vastly more because you're also carrying and accelerating all the fuel you already added. Ask for a modest speed, and the numbers stay reasonable. Ask for a great speed, and they explode. The mass of fuel you need can climb into the impossible, more fuel than the rocket could ever lift, more than could fit on the whole planet. This is why getting even a small capsule off the Earth takes those enormous towers of fuel we see on the launch pad. Watch a rocket rise, and nearly all of that towering machine is fuel and the tanks to hold it. The precious cargo at the very top, the part that actually goes somewhere, is a tiny sliver. Almost everything you are launching exists only to lift the rest of what you are launching. The Saturn V that carried people to the moon weighed nearly 3,000 tons at liftoff, and the small cone that came home held 3 people. That is the tyranny in a single image. A mountain of fuel for a handful of travellers. Now ask that same machine to reach not the moon, a mere 3 days away, but a star, 4 light-years off, at a speed measured in fractions of light itself. The equation gives an answer, and the answer is a wall. To push an ordinary rocket burning ordinary chemical fuel up to even a small fraction of light speed, you would need more fuel than exists in the entire solar system. Far more. You could turn every planet into propellant and still fall hopelessly short. Chemical rockets, the only kind that has ever flown, are simply not capable of interstellar travel. The mathematics closes the door before you begin. This is not a failure of engineering to be fixed with a better design. It is baked into how throwing mass to move works. If we ever want to reach the stars, we cannot simply build a bigger version of what we have. We need an entirely different way to push a ship, a way that does not drown in its own fuel. People have thought hard about this, and some of their answers are strange and bold. The first of them proposed to move a spaceship by setting off nuclear bombs behind it. In the years just after the Second World War, a small group of brilliant and slightly reckless minds asked a startling question. We had just built the most concentrated source of energy humans had ever made, the nuclear bomb. What if, instead of using it to destroy, you used it to fly? The project that grew from this idea was called Orion, and it ran through the late 1950s and into the 60s, backed by serious scientists including the physicist Freeman Dyson and the bomb designer Ted Taylor. The idea sounds like something from a fever dream, and yet the mathematics held together. You would build a large, sturdy spaceship with a thick metal plate on its underside called a pusher plate. Behind the ship, out the back, you would drop a small nuclear bomb. It would fall a little way and then detonate. The blast, a sphere of superheated plasma, would slam into the pusher plate and shove the whole ship forward. Then you would drop another bomb, and another, one every second or so, riding a steady string of nuclear explosions out into space. Great shock absorbers between the plate and the crew cabin would soak up each jolt, smoothing the violent shoves into something a human body could survive. You would quite literally ride the bombs. The strange thing is how well it would work. This was the great advantage. A nuclear explosion packs millions of times more energy, pound for pound, than any chemical fuel. By pushing with bombs, Orion sidestepped the tyranny of the rocket equation, because it was not carrying vast tanks of weak chemical fuel. It carried a magazine of compact, immensely powerful bombs. The designs on paper were enormous, some of them the size of small buildings, weighing thousands of tons, capable of carrying not a tiny capsule but a genuine crew with room to live. A version meant for the outer planets could have reached Saturn and returned within a few years, and the boldest versions looked further. Dyson himself sketched an interstellar Orion, a colossal ship pushed by hundreds of thousands of bombs that might reach a few percent of the speed of light. Not enough to make the crossing quick, but enough in principle to reach a nearby star across a span of centuries rather than tens of thousands of years. For a brief moment in the middle of the 20th century, a real path to the stars seemed to exist, drawn out in engineering diagrams by people who believed it could be built. It was never built, and the reasons are worth saying plainly. Setting off thousands of nuclear bombs in the atmosphere to launch from the ground would spread radioactive fallout across the sky, poisoning the very planet you were leaving, and in the year 1963 the major powers signed a treaty banning nuclear explosions in the atmosphere and in space, partly to slow the arms race. That treaty, sensible and humane, quietly closed the door on Orion. A ship that flew by detonating nuclear weapons had become, by international law, something you were not allowed to fly. So the bomb-driven ship remains on paper, a haunting what-if, a design that might genuinely have carried people toward the stars if the world had been a different place. Its core lesson survived, though. To reach the stars, you need the density of nuclear energy, not the weakness of chemical fuel. The next great design took that lesson and tried to harness the nucleus in a cleaner, more controlled way. Instead of exploding bombs, it would burn the same fire that powers the sun. If setting off nuclear bombs behind a ship felt too crude and too dangerous, there was a cleaner way to reach for the same enormous energy. And in the 1970s, a group of British engineers set out to design it properly. They worked under the banner of the British Interplanetary Society, a gathering of serious spaceflight enthusiasts, and over 5 years they produced the most detailed starship design the world had ever seen. They called it Daedalus, after the craftsman of Greek myth who built wings to fly. Their goal was strict and honest. They wanted a ship that could reach a nearby star within a single human working lifetime, about 50 years, so that the engineers who launched it might live to see its data return. They chose as their target not Alpha Centauri but Barnard's star, another near neighbour, about 6 light-years away, thought at the time to possibly hold planets. To cross 6 light-years in 50 years, the ship would need to reach roughly 12% of the speed of light. That is more than 30,000 kilometres every second, hundreds of times faster than the Parker Solar Probe. Nothing so fast had ever been seriously designed. The engine that would drive it burned the fire of the sun itself. This was fusion, the process that lights every star, in which small atomic nuclei are forced together to release a flood of energy. Daedalus would carry tiny pellets of fuel, a mix of forms of hydrogen and helium, and blast them, many times each second, with beams of powerful electrons. Each pellet would implode and ignite in a small burst of fusion, and a magnetic field would channel that burst out the back as thrust. It was, in a sense, Orion made fine and fast. Thousands of tiny controlled fusion sparks a second instead of great crude bombs. The ship would build up to its cruising speed over years of steady burning. The scale of it was staggering. Daedalus would have stood taller than most skyscrapers and weighed some 50,000 tons fully fueled. Most of that fuel, in 2 great stages that would fire one after the other and then be cast away. It was too large to build on Earth. It would have to be assembled in space and fueled from the atmosphere of a giant planet. And one of the fuels it needed, a rare form of helium, barely exists on Earth at all, and would have to be mined from the clouds of Jupiter by floating factories. The whole scheme sat at the very edge of imaginable engineering and beyond it in places. Here is the detail that matters most for our story, and the designers wrote it into the plan from the very start. Daedalus could never stop. It had no way to slow down at the far end. It would spend decades building up to 12% of light speed, and then it would simply coast, and when at last it reached Barnard's star, it would tear straight through the system at that same tremendous speed. In the few short hours of the flyby, it would fling out smaller probes, gather what data it could, and take its measurements as the star and any planets flashed past. Then it would fly on into the empty dark beyond forever, its work done in an afternoon. That was the honest bargain the designers accepted. Stopping was simply too hard, so they did not even try. Daedalus was a one-way arrow, meant to glimpse another star in passing and never to linger. It was never built, but it proved something important. A real starship could be sketched in real detail, and the next idea would try to shed the fuel entirely and let a ship be pushed by nothing heavier than light. Every design we have met so far drowns in the same difficulty. The ship must carry its own fuel, and the fuel weighs so much that it strangles the whole effort. So in the 1960s, a physicist named Robert Forward asked a freeing question. What if a starship carried no fuel at all? What if you left the engine at home and pushed the ship from behind with a beam of light? The idea rests on a real and slightly surprising fact. Light, though it has no weight, carries a tiny push. When sunlight lands on a surface, it presses on it, ever so faintly. You never feel this pressure in daily life because it is unimaginably gentle, far too soft to notice. But in the frictionless quiet of space, a gentle push that never stops can build into real speed over time. Spread a large, thin, mirror-bright sail and let light fall on it, and the sail will feel that steady press and begin, slowly, to move. This is a light sail, and unlike a rocket, it burns nothing and carries nothing. The push comes from outside. A sail pushed by ordinary sunlight would work near the sun, but out toward the stars the sunlight thins and fades, and the push dies away. Forward's real insight was to replace the sun with something we control. Instead of relying on scattered sunlight, you build an enormous laser, back home in our own solar system, and you aim its concentrated beam at the departing sail. The beam does not spread and fade the way sunlight does. It stays tight and fierce across huge distances, pouring its push onto the sail for as long as you keep it lit. The ship is pushed from behind by a spear of light thrown from home, and it accelerates without carrying a single drop of fuel. Forward worked the idea out in real detail through the 1980s, and the scale he arrived at was enormous. To push a crude starship this way, he imagined sails hundreds of kilometers across, thin as a soap film yet wider than a country, driven by lasers of almost unimaginable power, their energy gathered across the whole solar system. He even solved, on paper, the hardest part of any starship, the problem of stopping. His design used a sail built in rings. At the far end of the journey, the outer ring would attach and fly ahead, and the laser beam from home would bounce off it and reflect back onto the inner ring, pushing the ship the other way, slowing it down. Light from home would first speed the travellers up, and then, cleverly turned around, gently bring them to rest. It was beautiful, and it was almost absurdly demanding. The lasers Forward needed would draw more power than all of human civilization currently produces, focused and held perfectly steady on a distant sail for years on end. The sails had to be flawless, vast, and lighter than anything we can yet make. As a plan for tomorrow, it was pure fantasy. As a proof of an idea, it was profound. It showed that a ship need not carry its fuel, that the energy for the journey could stay behind and be sent as light across the dark. That single shift, leaving the power source at home, changed how people thought about reaching the stars. And decades later, a group of scientists and dreamers took Forward's idea and made it small. Instead of a vast sail carrying people, they asked what light could do to something no heavier than a paperclip. Their answer became the boldest starship plan of our own time. In the year 2016, the same year the planet around Proxima Centauri was announced, a group of scientists and wealthy backers stood up and declared that they would try, in earnest, to reach the stars within a generation. Their project was called Breakthrough Starshot. Among the names attached to it were the physicist Stephen Hawking and the investor Yuri Milner, who put real money behind it. And their plan took Robert Forward's dream of a light-pushed sail and shrank the ship down to almost nothing. The logic was simple and sharp. The reason starships are so impossibly hard is that they are heavy, and heavy things need monstrous amounts of push. So make the ship as light as physically possible. Do not send a great vessel with a crew and supplies. Send a chip. Starshot imagined a tiny spacecraft weighing about a single gram, no more than a large postage stamp, holding a camera, a power source, and a small radio, all etched onto a wafer the size of a fingernail. To this chip you would attach a sail only a few meters across and thinner than a sheet of paper. The whole thing together would weigh less than a coin. Then you push it with light. On the ground you build a vast array of lasers, thousands of them working as one, focused into a single beam of about 100 billion watts, an almost incomprehensible power, held on the little sail for just a few minutes. In those few minutes, the beam would drive the feather-light craft to about 1/5 of the speed of light. Not a few percent as Orion or Daedalus dreamed, but a full 20% of light speed, faster than anything humans have ever conceived of moving. At that speed, the tiny probe would cross the distance to Alpha Centauri in about 20 years. A person alive at the launch could live to see it arrive. That is the beauty of going small. A gram is easy to push. You do not fight the tyranny of fuel, because the sail carries none, and you do not fight great mass, because there is almost none to fight. The energy that would be hopeless for a heavy ship becomes merely enormous for a chip. And you would not send just one. You would send thousands of these tiny sails, a swarm of them launched over years, so that even if most were lost to dust or damage or bad luck, some fraction would survive the crossing and phone home from another star. The plan asks for real things we cannot yet do, and its designers are honest about them. No one has built a laser array anywhere near that powerful, or a sail that can take such a beam without tearing or burning, or a gram-sized craft that can survive 20 years in deep space and still send a whisper of a signal back across 4 light years. These are enormous problems, and Starshot is a long research effort, not a rocket waiting on a pad. But nothing in it breaks the laws of physics. It is hard, not impossible, and that alone sets it apart. There is one hard limit it does not even attempt to solve. Like Daedalus before it, the Starshot probe cannot stop. Racing along at 1/5 of light speed, it would blow through the Alpha Centauri system in a matter of hours, snapping what pictures it could as the stars and any planets flashed past, then hurtling on into the dark forever. A glimpse, gathered at tremendous speed, and then gone. It works precisely because it is tiny and never slows, and that is exactly why it can never carry a person. Everything that makes Breakthrough Starshot possible comes from one choice. The ship is almost weightless. A single gram is easy for light to push, easy to fling to 1/5 of light speed, easy to send by the 1,000. But the moment you want to send a person instead of a chip, every one of those advantages vanishes, and the whole problem transforms into something far larger. A human being cannot travel as a gram. A person needs air to breathe, and a sealed vessel to hold that air. They need water, and food, and warmth, and a way to carry away their waste, for every day of a journey that lasts decades. They need shelter from radiation, and space to move so their body does not waste away, and machines to recycle the air and water, and spare parts for those machines, and power to run all of it. A living human is not a payload of 1 gram. A vessel able to keep even a few people alive across a crossing of decades weighs not grams, but many thousands of tons, closer to a small ocean liner than a postage stamp. Now push that against the physics we have already met. To move a gram to 1/5 of light speed took a laser of 100 billion watts. The energy needed climbs in step with the mass you are pushing. A crude ship is not 1 gram but something like 1,000 million grams, 1 billion times heavier, and the energy to fling it at the same speed climbs by that same staggering factor. The laser array that could drive a chip becomes, for a crude ship, a machine drawing more power than the entire human species uses, sustained for years without fault. The gentle, elegant solution that worked so beautifully for a chip becomes, for a person, a wall of energy as tall as any we have met, and a person forces a second demand that a chip is spared. A chip does not care how long it flies. You can send it slow if you must and simply wait. It will not age or grow bored or die on the way. A person cannot wait forever. A human life is short. To reach another star within a lifetime, or even within a few lifetimes, the ship must go genuinely fast, a real fraction of light speed. So a crude starship must be both terribly heavy and terribly fast at the same time, and those two demands multiply against each other. Great mass is hard to push. Great speed is hard to reach. A person requires both at once, and the energy needed to satisfy them together is what turns a hard problem into a nearly unimaginable one. This is the quiet hinge of the whole story. The clever plans that seem to bring the stars within reach all work by sending something small and fast and unmanned, a chip, a probe, an arrow of instruments that glimpses another sun and flies on. They shrink the ship or skip the stopping or both. The instant you insist on a living human aboard, one who breathes and eats and must be kept alive and someday must slow down and land, every corner you cut reappears larger than before. The person is the heaviest cargo of all, not in kilograms alone, but in everything they need to stay a person. So a human crossing demands a heavy ship moving fast for decades, and a heavy ship moving fast for decades runs headlong into a danger we have not yet faced. At such speeds, even empty space stops being empty. The thin dust between the stars, harmless to a slow traveller, turns into something that can tear a fast ship apart. We tend to picture the space between the stars as perfectly empty, a clean and total nothing. It very nearly is. But nearly empty is not the same as empty, and at the speeds a starship must reach, that small difference becomes a matter of survival. The space between the stars is filled with an unimaginably thin haze of gas and dust, and a ship moving fast enough turns that gentle haze into a storm. Consider how thin it is. In the space between the stars, there is on average about 1 atom in every cubic centimetre, roughly 1 atom in a space the size of a sugar cube. Compare that to the air around you now, where a single cube of that size holds numbers of atoms too vast to picture. Interstellar space is emptier than the finest vacuum we can make in any laboratory on Earth. If you drifted through it slowly, you would never notice the scattered atoms at all. They are spread too thin to matter. Speed changes everything. When you move slowly through that haze, the occasional atom brushes gently against you. When you move at 1/5 of the speed of light, you slam into each atom with tremendous violence. It is the difference between walking through drifting mist and driving into rain at highway speed, then far beyond. A thing that was soft becomes hard purely because of how fast you meet it. At 20% of light speed, each lonely hydrogen atom the ship strikes arrives like a burst of radiation, a small blow of energy against the hull, and there are a great many of them across 4 light years. The gentle haze becomes a steady, scouring wind of particles, hammering the front of the ship every second of the crossing. Worse than the single atoms is the dust. Scattered through interstellar space are tiny grains, most far smaller than a speck you could see. To a slow traveller they are nothing. To a ship moving at 1/5 of light speed, a single grain of dust carries the energy of a small explosion, because energy climbs steeply with speed. 1 grain, no larger than a mote in a sunbeam, striking the ship at that velocity, could punch clean through metal or gouge a crater in the hull, and the ship cannot dodge them. They are too small to see coming and too many to track. It simply has to endure them, grain after grain, for the entire journey. This is why the front of any real starship would need to be armoured or shielded somehow, a thick barrier of material out ahead to absorb the endless rain of atoms and the occasional deadly grain. Some designs imagine a droplet of some substance held ahead of the ship as a disposable shield, or a thin cloud of particles thrown out in front to break up incoming dust before it strikes. Every solution adds mass, and mass, as we have seen, is the enemy. The faster you go to shorten the journey, the harder space itself hits back, and the more shielding you must carry, and the heavier and harder to push the ship becomes. The very speed that saves you also endangers you. For a tiny chip like Starshots, this may be survivable, since a probe is expendable and you can send thousands hoping some get through. For a ship carrying living people, who cannot be lost by the thousand, the thin dust of space becomes a genuine and constant threat. And it is not the only thing raining down on the travellers. Alongside the dust comes something invisible that no shield fully stops, and that works its harm not on the hull, but on the body itself. There is a rain in space that no wall fully stops, and it does its quiet damage not to the ship but to the living body inside. It is radiation, and on a journey lasting decades it becomes one of the gravest dangers a human crew would face, precisely because it never lets up and cannot be seen. We live our whole lives beneath two great shields, and we almost never think about them. The first is the Earth's magnetic field, an invisible cocoon reaching far out into space that catches and turns aside most of the charged particles streaming in from the sun and beyond. The second is the thick blanket of our atmosphere, which soaks up the rest before it reaches the ground. Together they keep us safe. Step outside those shields, out into deep space, and you stand exposed to the full flood of radiation that fills the galaxy, a flood our ancestors were always protected from. That flood has two sources. The sun throws off storms of particles, especially during its violent flares, and a sudden solar storm could deliver a dangerous dose to an unshielded crew within hours. But farther from the sun, out in interstellar space, the greater long-term threat comes from beyond our star entirely. These are the cosmic rays, atomic nuclei flung across the galaxy at nearly the speed of a light by distant exploding stars, arriving from every direction at once. They are fantastically energetic, and they pass through ordinary shielding as if it were barely there. A wall thick enough to stop them would be far too heavy to carry. What they do to the body is the trouble. Each cosmic ray that passes through a person is a tiny bullet tearing through living tissue, breaking apart the delicate molecules of the cell, damaging the long strands of DNA that tell the body how to repair and renew itself. A single passing ray does little, but out in deep space the rays never stop coming, day after day, year after year, each one leaving a little more damage behind. Over a journey of decades, that steady toll mounts. It raises the risk of cancer sharply, it can harm the heart and the blood vessels, and there is growing evidence from studies of animals exposed to similar radiation that it slowly injures the brain itself, dulling memory and thought over long exposure. This is the cruel arithmetic hidden in the phrase, a long journey. On Earth, time is mostly kind. The body heals and renews. In deep space, time becomes a slow poison, because every passing year is another year of radiation soaking into cells that can only repair so much. The travellers would not simply grow older on the way to Alpha Centauri. They would age faster and harder than they would at home, worn down by an invisible weather that no roof keeps out. The very length of the journey, the decades the crossing demands, is itself a wound. There are partial answers. You might wrap the crew's quarters in the ship's own water and fuel and waste, using the mass you already carry as a shield. You might hollow out a small storm shelter, thick-walled, where the crew could huddle during the worst solar bursts. But against the ceaseless cosmic rays from the wider galaxy, no shelter is complete, and every added layer is more mass to push. The radiation, like the dust, cannot be fully escaped. only endured. Suppose, though, that a crew survived it all, the dust, the rays, the long years. Suppose they crossed the whole gulf and arrived at last within sight of another star. They would then face the hardest problem of the entire voyage, harder even than leaving. They would have to stop. Imagine a crew has done the impossible. They have crossed 4 light years of dust and radiation, and decades of dark, and ahead of them, growing brighter each day, is another sun. The hardest part of the whole journey still lies before them. Before they can do anything at all, before they can orbit a planet or send a lander down or simply look, they have to stop. And stopping, it turns out, may be the single hardest thing a starship ever has to do. Think about what it took to get up to speed. To reach 1/5 of the speed of light, a ship needs a staggering push, whether from bombs or fusion fire or a beam of laser light thrown from home. All of that effort goes into speeding up, but the universe offers no free breaks. To slow back down at the far end, you must undo every bit of that speed, and undoing it costs, very roughly, as much energy as building it up did in the first place. You do not just need enough power to reach the stars, you need enough to reach them, and then to cancel all that motion again. Essentially 2 enormous journeys worth of energy for 1 round of travel out. This is exactly why the boldest real designs simply refuse to stop. Daedalus was built as a flyby from the start, tearing through its target system in a matter of hours. Breakthrough Starshot's tiny sails would blow past Alpha Centauri at 1/5 of light speed, gathering a few hours of data before racing on into the dark forever. For an unmanned probe, this is an acceptable bargain. A glimpse is still worth having, and a machine does not mind flying on into nothing. It gets its pictures in a single afternoon and never needs to slow. For a person, a glimpse is not enough. You do not spend a lifetime, or many lifetimes, crossing to another star only to flash past it in an afternoon and vanish into the void beyond. A human crew must slow down and match speed with a planet and settle into orbit and stay. And that means the ship must carry or somehow find the means to shed all its tremendous speed after decades of crossing. It doubles the impossible. Every hard number we have met, the fuel, the energy, the mass, must be paid twice. Once to go and once to stop. People have dreamed up ways to brake without carrying twice the fuel, and some are genuinely clever. Robert Forward's stage sail would catch reflected laser light from home and turn it around to slow the ship. Other designs imagine unfurling a vast magnetic sail that drags against the thin gas of the destination system, or against the wind of particles streaming off the target star, using the very haze that threatens the ship as a gentle, endless brake to bleed off speed over years. These are ingenious ideas, and every one of them is harder than it sounds, and none has ever been tested even in small ways. So we arrive at the shape of the trap. Going fast enough to reach another star within a human span is barely maybe imaginable. Going fast and then stopping is far beyond that. It is easier, always, to throw something past a star than to bring it gently to rest there. And this simple, stubborn fact begins to bend the whole question of a human journey. If stopping is so brutally hard, then perhaps a starship is not meant to make a round trip at all. Perhaps it can only ever go one way. And if a ship can only go one way, then coming home is not merely difficult. It may be, from the very first, out of the question. We just met the brutal fact that stopping a starship costs about as much as launching it. Now follow that thought one step further, to the idea of coming home again, and watch the numbers climb past every wall we have already met. A return trip is not twice as hard as a one-way trip. It is far more than twice, and understanding why is the heart of this whole story. Break the round journey into its 4 separate pieces. First, you must speed up, here at home, to 1/5 of the speed of light. Second, having crossed the gulf, you must slow all the way back down to arrive at the far star. Third, when it is time to leave, you must speed up all over again, out there, 4 light years from any help. And fourth, you must slow down one final time to arrive safely back at Earth. 4 separate rounds of enormous acceleration, where a one-way flyby needed only one and a one-way landing needed two. Each of those pieces carries the full staggering cost we have already seen, and they do not simply add together, they multiply in a way that runs away from you fast. Here is why. To slow down at the far star, you must carry the fuel for that braking all the way across the Gulf, which means speeding up that extra fuel too at the start. To speed up again for the trip home, you must carry that fuel across as well and slow it down at the destination, and it needs its own fuel to move it, which needs its own fuel in turn. Every leg of the trip must haul the fuel for every leg that comes after it. The demand does not stack gently, it compounds, each stage feeding the next until the total swallows any ship you could ever build. This is the tyranny of the rocket equation from Chapter 9, returning now with far greater force. There it merely made reaching the stars hard. Here, applied 4 times over and folded on itself, it makes a round trip effectively impossible. If a one-way crude crossing sits at the ragged edge of what physics might someday permit, a round trip sits far past that edge, out in the plainly unreachable. The fuel to bring a crew home again is more than the fuel to send them, many times more, and the fuel to send them was already more than we know how to gather. So the arithmetic hands us a quiet, heavy conclusion, and it is the one this whole video is built around. Even if we someday learn to send human beings to Alpha Centauri, we will almost certainly never be able to bring them back. The energy simply is not there, and the shape of the mathematics says it may never be, no matter how our engineering improves. A journey to the nearest star is not a voyage with a return leg, it is a departure. The travellers would be leaving, in the fullest and most final sense of that word. And this changes what the journey even means. It is no longer a mission, in the way we send astronauts to the space station and welcome them home. It becomes a migration, a leaving behind, a one-way passage into the unknown. Everyone aboard would be saying goodbye to Earth forever, not as a risk they accept, but as the plain and permanent condition of going at all. And that is only the arithmetic of fuel. There is another toll waiting, stranger than fuel, woven into the fabric of time itself. It has to do with what happens to a clock that travels very fast. There is a stranger toll waiting on any fast journey, one that has nothing to do with fuel and everything to do with the deep nature of time. It comes from Albert Einstein and from the theory of relativity he laid out in the year 1905, and it is one of the most thoroughly tested ideas in all of science. Put simply, time does not flow at the same rate for everyone. It depends on how fast you're moving, and on a starship moving at 1/5 of the speed of light, that quiet fact becomes real and personal. Here is what Einstein discovered. The faster you travel through space, the slower your clock ticks, compared to the clocks of those you leave behind. This is called time dilation, and it is not an illusion or a trick of measurement. It is the way the universe is built. Time itself runs slower for a fast-moving traveller. A clock on a fast ship, a heartbeat, the aging of a body, all of it genuinely slows relative to the same things back on Earth. The traveller does not feel it. To them, their own clock ticks along as normal, a second is a second, a day is a day. It is only when the traveller and the stay-at-home compare their clocks afterward that the gap appears. We know this is true because we have measured it, again and again, in careful experiments. Precise atomic clocks flown around the world on ordinary airplanes come back very slightly behind clocks that stayed on the ground, by exactly the amount Einstein's mathematics predicts. The satellites that run the navigation in your phone move fast enough that their clocks drift measurably from ours, and engineers must correct for it constantly, or the maps would quickly go wrong. Time dilation is not exotic speculation. It is a daily engineering fact, built into machines you already use. At the speeds we travel in daily life, the effect is far too small to feel, a matter of billionths of a second. But at 1/5 of the speed of light, it grows into something you could notice, though it is still gentle at that speed. A crew crossing to Alpha Centauri at 20% of light speed would age slightly slower than everyone they left behind. On a crossing that takes about 21 years as measured from Earth, the travellers might experience something closer to 20 years, a difference of months, not decades, at that particular speed. Real, measurable, but modest. The effect only becomes dramatic as you push closer to the speed of light itself. A ship moving at 99% of light speed would see time slow by a factor of 7. Push to 99.9%, and the traveller's clock crawls more than 20 times slower than Earth's. At such speeds, a journey that takes centuries as seen from home might pass in only years for those aboard. We are nowhere near able to fly that fast. But the principle holds, and it means the faster a starship could ever go, the more sharply its travellers would slip out of step with the time back home. This gentle slowing of the traveller's clock does something profound to the whole idea of a journey and a return. If the person who leaves ages more slowly than everyone they left behind, then they and their home are no longer keeping the same time, and that leads to one of the most haunting thought experiments in all of physics, a story about two people who begin exactly the same age. Let me make Einstein's quiet toll into something you can feel in the body, through the oldest and most haunting thought experiment in physics. It is called the twin paradox, and it has been argued over for more than 100 years, since the early days of relativity itself. Imagine two twins, born on the same day, the same age in every way. One of them becomes an astronaut and boards a starship. The other stays home on Earth, and what happens to them is genuinely strange. The travelling twin flies out to a distant star at very high speed and then turns around and comes home. Because they move so fast, their clock ran slow the whole way, exactly as we just saw. So when the ship lands and the two twins stand face to face again, they are no longer the same age. The twin who travelled is younger than the twin who stayed. Not in feeling, not in some vague way, but in plain biological fact. Fewer years have passed for the one who flew. They have lived less time. The stay-at-home twin might be grey and lined, while the traveller is still visibly younger, having aged only a fraction as much. This is not science fiction, and it is not a paradox in the sense of a contradiction, though the name has stuck. It is a real, tested consequence of how time works. The reason it feels like a paradox is a fair question that troubled people for years. If motion is relative, if either twin could claim to be the one sitting still while the other moves, then why does only one of them come back younger? The answer is that the two situations are not truly the same. The travelling twin is the one who feels the great push of acceleration, who speeds up and turns around and slows down. The stay-at-home twin feels none of that. That difference, the turning around, breaks the symmetry, and settles clearly which twin ends up younger. It is the one who made the journey. Now stretch this from the mild speeds of Alpha Centauri to the edge of what physics allows, and it becomes almost unbearable to imagine. A twin who flew to a distant part of the galaxy at very close to light speed and came home might have aged only a few years, while on Earth centuries had rolled past. They would step off the ship into a world where everyone they knew was long dead, where the language had shifted and the maps were redrawn, still young themselves, carrying the memory of a home that no longer existed. The traveller would have outrun time and paid for it by losing everyone. For a crossing to Alpha Centauri, the effect is small, only months of difference. The twins would still recognise the world when the traveller returned, if returning were even possible. But even that small gap points at something profound. To travel fast is to step, however slightly, out of the shared river of time that carries everyone else along. The faster and farther you go, the more you drift from the moment your loved ones are living in. And this is only what happens to the clocks. Something else changes on the long crossing, something that needs no relativity at all to bite. Even if the ship's clock and the Earth's clock ran in perfect step, the sheer number of ordinary years the journey takes would be enough to transform the home the travellers left behind. Set aside Einstein for a moment, and the subtle bending of clocks. Forget time dilation entirely. Even if the traveller's clock and the Earth's clock ran in perfect step, the plain length of the journey would still transform everything. A crossing to Alpha Centauri takes decades at best, and the world does not pause while the travellers are gone. It moves on without them, and by the time they arrive, the home they left has quietly become a different place. Picture the fastest crewed crossing anyone seriously imagines, something like 20 years each way at a fifth of light speed. 20 years is not a long time in the life of a star, but it is a great span in the life of a world. Think back over the last 20 years of your own life, and how much has changed. New leaders have risen and fallen, cities have grown and neighbourhoods have been rebuilt. Whole industries have appeared that did not exist before, and others have vanished. The music is different, the words people use are different, the small texture of daily life has shifted in 1,000 ways. All of that would happen at home while the travellers were simply in transit, seeing none of it. And that is only the swiftest imaginable trip. Most realistic crossings would take far longer, a century or several, and over a century the change becomes almost total. The travellers would leave one world and arrive in effect in the future. Everyone they knew and did not bring with them would have grown old and died. The children they waved goodbye to would be long gone, their grandchildren strangers. The nation they departed from might no longer exist, replaced by something with a different name and different borders. The technology back home would have raced ahead, so the ship itself, a marvel at launch, might arrive already ancient and outclassed by things built long after it left. There is a strange twist hidden in that last thought, sometimes called the weight paradox. Suppose you launch a starship at the very best speed your century can manage. It sets off on its long crawl, but back home, invention keeps racing forward. 100 years later, a far faster ship could be built, one that might overtake the first vessel partway across the Gulf and reach the destination well ahead of it. The earliest travellers could, in principle, arrive to find people already there, people who left long after them, but flew faster and passed them in the dark. The first to leave need not be the first to arrive. All of this deepens the one-way nature of the journey in a way that has nothing to do with fuel or physics. Even if, somehow, you could bring the travellers home, there would be no home left to return to. The world that launched them would be gone, aged out of existence by the simple passage of ordinary years. They would come back as visitors to a future that had no place set for them, strangers wearing the faces of people everyone had already mourned and forgotten. To leave for the stars is to leave not only a place but a time, and neither one waits for your return. And while the travellers are out there, drifting further from the world they knew, they would still, at least at first, try to stay in touch. They would send messages home and listen for messages back. But even that thread, the simple act of talking across the gulf, breaks down in a way that quietly ends any ordinary sense of connection. Of all the ways the distance to Alpha Centauri separates a traveller from home, the gentlest to describe and the strangest to live with is this. You could not have a conversation. Not a real one, not the back and forth we mean by the word. The distance is so vast that even a message moving at the speed of light, the fastest anything can travel, takes more than 4 years to cross it. And that single fact quietly ends ordinary talk forever. Think about what a conversation actually is. You say something. The other person hears it almost instantly, thinks and replies, and you hear their reply just as fast. Even a phone call across the whole Earth feels immediate, because light circles the planet many times in a single second. We're so used to this that we never notice it. Distance for talking has always been nearly free. The words arrive as fast as we can speak them. Now stretch that line of talk across 4¼ light years. You send a greeting from the ship toward Earth. It races away at the speed of light, and it takes more than 4 years to arrive. Someone on Earth hears it and sends an answer back, and that answer takes more than 4 years to return to you. From the moment you say hello to the moment you hear the reply, more than 8 years have passed. Ask a simple question, and you wait most of a decade for the response. There is no conversation possible across such a gap. There is only a slow exchange of letters, each one arriving from a sender who is, by the time you read it, more than 4 years older, and possibly no longer even there. This severs something we rarely think to name, the sheer immediacy of being in touch. The travellers could still send word home, and receive word back, but every exchange would be a message from the deep past. News from Earth would always be more than 4 years stale by the time it reached the ship, and would grow staler with every kilometre of distance the ship added. A crew a full light year out would wait years to learn of a death in the family, and their words of grief would take years more to arrive, spoken to people who had long since finished mourning. The thread of connection would not snap cleanly. It would stretch and thin and slow until it was less a conversation than a scattering of old letters crossing in the dark. And as the ship travelled farther, even that would fade, cross the full distance to Alpha Centauri, and the delay each way settles at more than 4 years, fixed by the width of the gulf. But the sense of belonging to the same living moment, the feeling that your words and theirs share a single present, would be gone from very early on. The travellers and the Earth would drift into separate nows, each living years apart from the other, forever out of step. So the isolation of the journey is not only a matter of empty space and long years, it reaches into the simplest human thing, the wish to speak and be answered. The travellers would be more alone than anyone in history, cut off not by silence but by the slow crawl of their own words across the dark. And once you accept that the journey is one way, and this long, and this lonely, a hard question follows. How could anyone survive a crossing that lasts not years but centuries? The answer people have imagined is a ship that stops being a ship and becomes a world. If the crossing to another star takes not years but centuries, then no single crew could live to see both ends of it. The people who left Earth would die in the dark long before arrival, with the destination still generations away. So people who think seriously about interstellar travel have imagined a different kind of ship, one built not for a journey, but for a life. It has a plain and haunting name. It is called a generation ship. The idea is this: if you cannot make the trip short, you make the ship into a place where many human lifetimes can unfold. You build not a cramped capsule but an enclosed world, large enough to hold a whole community, with everything they need to live and to raise children and to grow old. The first generation boards knowing they will never arrive. They will live their whole lives aboard, and die aboard, and be replaced by their children, who are born in flight and live and die the same way. Generation after generation is born, lives, and passes, all inside the moving ship, until at last some distant descendant, many greats removed from the ones who left Earth, arrives at the far star. The ship carries not travellers, but a lineage. To make this possible, the ship must be genuinely a world. It would need to be enormous, likely spun to create a feeling of gravity by its own rotation, so that bodies and bones do not waste away over the long crossing. It would need farms to grow food, and a way to recycle every breath of air and every drop of water endlessly, for centuries, because nothing new can be brought aboard once the journey begins. Everything the community will ever use across all those generations must either be carried from the start or made and remade inside the ship. It becomes a closed loop, a tiny sealed biosphere, a piece of earth wrapped in metal and sent very slowly across the dark. The challenge is not mainly one of engineering. It is one of keeping a small, closed world alive and whole for a span longer than most nations have existed. A generation ship crossing at a speed our machines might someday reach could take many centuries, perhaps 1,000 years or more. For all that time, a few hundred or a few thousand people must sustain not only their bodies, but their knowledge, their skills, their reasons for going. Every machine that fails must be repaired by someone who understands it, using only what is aboard. A single generation that forgets how to run the ship, or loses the will to keep it running, could doom everyone who comes after. And the numbers of people matter in a way that is easy to miss. The community cannot be too small, or over centuries of isolation it would grow frail and inbred, its children weaker than their parents. Careful studies suggest a generation ship would need at least a few hundred people, and more likely a few thousand, to stay genetically healthy across such a span. So the ship must be large enough not merely to carry people, but to carry a whole living population, breeding and renewing itself for a journey longer than recorded history. The generation ship solves the problem of time by accepting it fully and passing the journey down like an inheritance. But it raises a question sharper than any equation, one about the people who never chose to go at all. It is about the children born in the dark between the stars. The generation ship carries not one crew, but a chain of them, each born, living and dying in flight. And that raises a question that no amount of engineering can answer. A question that is not about machines at all, but about people and about consent. The first generation chooses to go. They stand on the deck, look back at Earth, and decide freely to leave forever. But their children do not choose, and their children's children choose even less. They are simply born somewhere in the long dark between the stars into a moving world they had no say in boarding. Think about what such a child would know. They would be born inside the ship, and the ship would be the whole of their world. They would never have walked on open ground, or felt rain, or looked up at a real sky. Earth would be a story to them, a blue point of light dwindling behind, or gone from view entirely, known only through pictures and records and the memories of grandparents who themselves grew fainter with each passing year. The destination star would be another point of light, still decades or centuries ahead, a place they too would never reach. They would live their entire lives in transit, born between two worlds, belonging fully to neither. There is something quietly heavy in this. The people who launch a generation ship make a choice for hundreds of descendants who cannot object, committing them all to a life sealed inside a moving vessel with no open sky and no way off. Those descendants inherit the journey the way we inherit the century we are born into without being asked. Some might embrace it and find deep meaning in carrying the mission forward. Others might resent it bitterly, might wish with their whole hearts that their ancestors had stayed home, and yet have no way at all to undo the choice that placed them there. There is no turning the ship around. The decision, once made, binds every generation that follows, and the mission itself would rest entirely on faith, kept across time. The first generation must trust that their great-great-grandchildren will still care about arriving, will still tend the farms and mend the machines and remember why the whole voyage began. But people change across centuries. Whole societies forget their founding purposes in far less time. A generation born in the ship, who never knew Earth and will never see the destination, might simply lose interest in a goal that belongs to strangers long dead and descendants not yet born. The ship could arrive at last with no one aboard who remembers or cares what it was sent to do. Some who study this call it the deepest problem of the generation ship, deeper than any question of fuel or shielding. It is the problem of holding a purpose and a working world together across a span longer than any human institution has ever lasted. The bodies might survive the crossing. Whether the mission, the knowledge and the will survive it is a different and harder thing. And there is another change these children would carry, one written not in their minds but in their flesh, a body that grows up far from Earth, in weak gravity and sealed air, does not stay the same body that left. Over the long crossing, the human form itself would begin, slowly and certainly, to change. The people aboard a starship would not arrive as the same kind of creature that left. A human body is shaped, in every fibre, by the world it grew up on, and chief among the forces that shape it is gravity. We are built for the steady pull of Earth, and take it so completely for granted that we never feel it as a force at all. Remove it, or weaken it, for years on end, and the body begins quietly to come undone. We know this is true because we have watched it happen to astronauts in far shorter times than any journey to the stars. Start with the bones. On Earth, your skeleton is under constant gentle load, and it responds by staying strong, rebuilding itself day after day to bear your weight. Take that weight away, as happens in the weightlessness of space, and the body reads the message that the bones are no longer needed at full strength. It begins to dissolve them. Astronauts on the space station lose bone at a rate of about 1% every month, month after month, their skeletons slowly thinning like those of a very old person, only far faster. Over years, the loss would be severe. Bones that lose enough substance grow brittle and break under loads they once carried easily. The muscles follow the same sad logic. A muscle that does not work grows weak, and in weightlessness, the great muscles of the legs and back, the ones that hold you upright against gravity, barely work at all. They shrink and soften. The heart itself is a muscle, and it too has less to do when blood no longer has to be pumped upward against gravity, so it weakens and grows smaller. Astronauts must exercise for hours every single day just to slow this decline, strapping themselves to machines that fake the resistance their bodies no longer feel. And even with all that effort, they return to Earth weakened, sometimes unable to stand at first, needing weeks or months to recover. Other changes are stranger still. Without gravity to pull fluids down into the body, they gather in the upper body and head, puffing the face and pressing on the eyes, and long missions have left astronauts with lasting changes to their vision. The heart and blood vessels forget how to handle the pull of gravity. The very sense of balance tuned to a world with a clear up and down grows confused. Every system that quietly assumed the presence of Earth's pull must adjust to its absence, and none of them adjust perfectly. This is why a serious starship would likely spin, to press its crew outward against the floor and mimic the weight of home, as we saw with the Generation ship. But even a spun ship might only manage a fraction of Earth's gravity, or a version of it that feels subtly wrong, and children raised in it would grow into that lesser pull. A person born and raised in low gravity might grow taller and thinner, with a weaker skeleton, a body that had never once known the full weight of Earth and could perhaps never survive it. Set foot on Earth, and their own home planet might crush them, its gravity too strong for a frame that grew up without it. They would be human still, but reshaped by the journey into something Earth itself could no longer hold. And this reshaping would not stop at bone and muscle. It would reach even into the invisible life we carry within us, the vast community of tiny organisms that lives inside every human body, and that too would begin to drift away from its earthly roots. The changes a starship works on the human body reach deeper than bone and muscle, all the way down to a part of ourselves we cannot see and rarely think about. Every human being is not a single creature but a walking community. Inside you, and on your skin, live trillions of tiny organisms, mostly bacteria, so many that they rival the number of your own cells. This hidden crowd is called the microbiome, and it is not a passenger you could leave behind. It helps digest your food, trains your immune system, and quietly shapes your health in ways we are only beginning to understand. Wherever humans go, this invisible community goes too. On a starship, that community would find itself in a strange new home, and it would begin to change. The microbiome we carry was shaped over millions of years by life on Earth, by the soil, the animals, the plants, the open air, and the endless mixing of people and places. A sealed ship has none of that. It is a small, closed world, scrubbed and controlled, with the same recycled air and the same limited set of surfaces and foods, year after year. Cut off from the rich variety of Earth, the mix of organisms inside the crew would slowly narrow and shift, drifting away from the balance their bodies evolved to expect. We have already seen the beginnings of this on the space station. Studies of astronauts show that their internal community of microbes changes during long missions, some kinds fading, others rising. The station itself develops its own population of microbes, spread from the crew across the walls and equipment, a small ecosystem living alongside the humans. In the tight enclosed quarters of a starship, over years and generations, this drift would go much further. The travellers would carry a version of Earth's inner life that grew steadily less earthly with every passing year, adapting to the ship as surely as the people did. For children born aboard, the change would be deepest of all. A baby is not born with its microbiome. It gathers that community fresh from its mother and from the world around it in the first days and years of life. A child born on a starship would gather its inner life not from the soil and animals and open landscapes of Earth, but only from the sealed world of the ship and the people already aboard. Whatever mix of organisms had drifted and narrowed by then is all the child would receive. Each generation would pass down a slightly different, slightly thinner inner ecosystem to the next, and over a long enough voyage the crew's microbiomes might become something meaningfully distinct from any that exists on Earth. Why does this matter, beyond curiosity? Because this hidden community is woven into our health in ways we do not fully grasp. A microbiome that drifts too far from its natural balance can bring trouble, weakening digestion, disturbing the immune system, opening the door to illness. The travellers, and especially the children born along the way, might face health problems rooted in a part of themselves no one can see, adrift from the living world that shaped it. They would be changed not only in their bones and muscles, but in the very ecosystem they carry inside. So the journey would reshape the travellers outwardly and inwardly, in body and in the hidden life within. But perhaps the hardest change of all is none of these. It is the one that happens in the mind, in the simple, crushing awareness of how far from home you truly are. We have followed how the journey would change the body and the hidden life within it. But perhaps the heaviest burden of a voyage to another star would fall not on the body at all, but on the mind. Human beings are not built for the kind of distance and confinement a starship demands, and the psychology of such a journey may prove as great an obstacle as any wall of fuel or radiation. Begin with the confinement itself. The crew would live their entire lives, or a large part of them, inside a single sealed vessel. The same walls, the same faces, the same rooms, day after day, year after year, with no way out and nowhere new to go. We have small glimpses of what this does to people, from submarine crews sealed underwater for months, from researchers wintering over in the deep isolation of Antarctica, from astronauts on long stays aboard the space station. Even in these far shorter confinements, people report a familiar set of troubles. Tension rises between crewmates over the smallest things, moods darken, sleep suffers. A strange listlessness can set in, a fading of drive and interest that researchers have come to expect on long isolated missions. Now stretch that from months to decades, or to a whole life. The Starship crew would face something no submarine or polar station ever has, a confinement with no scheduled end, no date circled on a calendar when they finally come home. For a generation ship, there is no coming home at all, not for anyone aboard, not ever. The crew would have to build a whole life and find real meaning in it, inside a moving box drifting through emptiness, knowing the walls around them are the only world they will ever have. And then there is the distance itself, and what it might do to a mind to truly grasp it. Astronauts who have gone no farther than the moon speak of looking back at the Earth, that small blue marble, and being changed by the sight, filled with a piercing sense of its fragility and preciousness. But the Earth was still right there, close enough to shelter the whole of their world in a single glance. The travellers to Alpha Centauri would watch that blue marble shrink to a mere point of light among the stars and then vanish altogether, indistinguishable from all the rest. There is a term some have offered for the dread this might bring, a kind of homesickness beyond any we know, the crushing awareness of being utterly, permanently cut off from the world that made you. No one has ever felt distance like that, and we cannot fully know what it would do to a person. It might break some. It might in others give way to a hard-won peace, an acceptance of the ship as home and the mission as purpose. Humans are remarkably able to adapt, to make a life wherever they find themselves, to grow attached to even the harshest place if it is the place they know. But it would ask something of the mind that has never been asked of anyone, to let go of Earth entirely and belong instead to a small world in motion, with the whole of home reduced to a story and a fading light. All of these burdens of body and mind gather toward a single moment on the journey. There comes a point, out in the dark, when turning back stops making any sense at all. It is worth finding exactly where that point lies. Somewhere out in the dark, on the long crossing to Alpha Centauri, there is a line. You cannot see it. Nothing marks it. But once the ship passes it, going home stops making any sense at all. Before that line, turning back is at least thinkable. After it, the destination is closer than the Earth, and there is no reason left to turn around. It is called the point of no return, and finding roughly where it lies makes the one-way nature of this journey feel real in a new way. The idea is familiar from smaller journeys. A pilot flying across a wide ocean reaches a moment, somewhere past the middle, when they no longer carry enough fuel to turn back to the airport they left. From that moment on, the only choice is forward to the far shore. The point of no return is simply the place where going back costs more than going on. For an ocean flight, it sits near the midpoint, adjusted for winds. For a starship, the same logic applies, stretched across light years. For a ship that must slow down and stop at the far end, the point of no return lies near the halfway mark of the journey. Before the midpoint, if something went wrong, you could in principle turn the ship and limp back toward Earth. Past the midpoint, Alpha Centauri is nearer than home, and turning back would only add years and cost more of everything you have. The rational choice becomes to press on. Halfway across, more than 2 light years out, the door to Earth quietly closes, not with a slam but with simple arithmetic. But for the fast, one-way starships we have mostly been discussing, the ones that never carry the means to stop at all, the point of no return comes far sooner and far harder. A ship built like Breakthrough Starshot or like Daedalus spends its early years accelerating up to 1/5 of light speed, and then it cannot stop by design. It carries no way to shed that speed. For such a ship, the point of no return arrives the moment it finishes accelerating. Once it is up to full cruising speed, with no fuel left to brake or turn, it is committed utterly. It will pass through the destination and fly on forever, and nothing aboard can change that. The point of no return is not the midpoint. It is very near the beginning. There is something quietly sobering in this. We imagine the great drama of such a journey lying at the far end, at the arrival, at the new world. But the truest moment of commitment might come early and pass almost unnoticed. A switching off of engines, after which every soul aboard is bound to the crossing whether they like it or not. From that instant, Earth is no longer a place they could return to, even in principle. It is only a place they came from, receding behind them at 1/5 of the speed of light, growing more unreachable every second. And once you have crossed that line and pressed onto the far star, a final truth settles over the whole endeavour and changes what it was ever about. If you cannot come back, and cannot even slow down without extraordinary measures, then reaching another star was never really a visit. Arrival, it turns out, does not mean stopping by. It means staying, for good. Everything we have followed, the fuel that cannot be doubled, the years that cannot be shortened, the speed that cannot easily be shed, the home that will not wait, gathers now into a single plain conclusion. To reach another star is not to visit it. It is to stay. Arrival and settlement are the same act. There is no version of this journey where you go, have a look, and come home to tell the tale. If you arrive at all, you arrive to remain. This turns the whole idea of interstellar travel into something quite different from the space travel we know. When astronauts go to the space station, or when we picture people walking on Mars, we imagine a trip, with a departure and, crucially, a homecoming. They go, they do their work, they return to Earth and to the people who waited. That shape, the round trip, is so deep in how we think about travel that we hardly notice it. Going somewhere means, almost by definition, being able to come back. Alpha Centauri breaks that shape completely. The arithmetic of fuel makes a return effectively impossible, as we saw. The difficulty of stopping means many ships would not even pause at the destination, let alone turn around. And the sheer passage of time means that even if you could somehow return, the Earth you left would be gone, aged into an unrecognizable future. Every path leads to the same place. Whoever crosses to Alpha Centauri crosses it once, in one direction, and whatever they find at the end is where they will spend the rest of their lives. So the people who go would not be explorers in the old sense, the kind who plant a flag and sail home. They would be settlers, or they would be nothing. Their task would not be to reach Alpha Centauri and report back. It would be to arrive and to build a life there and to make of that new place a home, because no other home would ever again be open to them. The mission would not end at arrival. Arrival would only be the beginning of the true work, the work of staying alive and putting down roots around another sun. This casts even the destination in a harder light. It is not enough for Proxima b or any world we aim for to be worth a glance. It would have to be worth a life, and the lives of all the descendants who follow. A barren rock that a passing probe might photograph and leave behind is no place to strand a human colony forever. For a one-way human journey to make any sense, the destination must be somewhere people could actually live and thrive and raise generations. The bar is not can we reach it. The bar is could we stay. And once you see the journey this way, as a permanent leaving rather than a bold excursion, something unexpected happens. It stops looking like science fiction and starts looking strangely familiar, because human beings have done this before, not across light years, but in spirit, again and again, throughout our whole history. The one-way journey into an unknown land with no way back is not a new idea at all. It may be one of the oldest patterns we have. The idea of a journey with no return can sound like the bleakest kind of science fiction. But step back from the stars for a moment and look at our own history, and you find that the one-way journey is not strange to us at all. It is one of the oldest and most human things we do. Long before anyone dreamed of other stars, people were leaving home for good, walking into the unknown with no thought or possibility of coming back. The permanent migration is woven all through the story of our species. Begin at the very beginning. Our distant ancestors arose in Africa, and then, over many thousands of years, they walked out of it and spread across the entire planet. These were not round trips. A band that crossed a mountain range or a desert into new land did not turn around and report home. They kept going, generation after generation, and their descendants filled Asia and Europe and eventually every habitable continent. Each step into new territory was, for the people taking it, a door that closed behind them. They could not go back, and they did not try. They simply made a home wherever they arrived, and moved on again when the time came. The peopling of the Pacific is perhaps the closest echo of a starship voyage in all of human history. Across the vast emptiness of that ocean lie thousands of tiny islands, separated by enormous stretches of open water with no land in sight. And people reached them in outrigger canoes, sailing deliberately into the blank horizon with no certainty that anything lay ahead. They carried with them everything a new colony would need: plants to grow, animals to breed, the knowledge to start a whole society from nothing. When they found an island, they settled it, and often that was that. No return to the home they had left, sometimes for many generations, sometimes never. They crossed their own kind of empty dark on faith to plant human life on a distant, unknown shore. The pattern repeats through recorded history as well. Think of the great waves of people who crossed oceans to settle new lands, boarding ships knowing they would almost certainly never see their birthplace or their families again. For most of them, the crossing was final. The journey took months and cost everything and offered no way back. They said their goodbyes as permanent goodbyes and stepped aboard anyway, choosing a new and uncertain life over the known one they were leaving behind. To go was to leave forever, and countless people across every era and continent chose exactly that. Seen against this long history, a one-way journey to the stars looks less like a break with human nature and more like its furthest expression. We are, and always have been, a species that leaves. We push into the unknown, accept that the door closes behind us, and build a home on the far side of the crossing. The distances change, from a valley to an ocean to the gulf between suns, but the essential act is old and familiar. A voyage to Alpha Centauri would be the same ancient human story, told at a scale our ancestors could never have imagined. But there is one honest difference between those old crossings and the leap to the stars, and it shapes who or what we would really send first. Our ancestors sent themselves because they had no other choice. We do, and that changes everything about the first messengers we would send toward another sun. For all we have said about human travellers, about generation ships and settlers and children born in the dark, there is an honest truth we should face plainly. When we finally do send something toward Alpha Centauri, it will almost certainly not be a person. It will be a machine. The first emissaries from Earth to another star will be robotic, small and unmanned, and they will go long before any human being does, if a human ever goes at all. The reasons are all the ones we have gathered along the way. A machine does not need air or water or food or warmth. It does not age in any way that matters, so a journey of decades or centuries is no hardship to it. It does not suffer the loneliness of the crossing, or the crushing distance from home, or the slow poison of radiation in the way a living body does. Though radiation can still damage its electronics, it does not need to come back, and feels no loss in staying, and above all, it can be small. A probe like Breakthrough Starshot's tiny sail weighs a single gram, and that is exactly why it might actually be sent within our lifetimes. Everything that makes a human crossing nearly impossible, the mass, the life support, the return trip, simply falls away when the traveller is a machine. This is why every serious near-term plan to reach another star sends robots, not people. Breakthrough Starshot aims to fling a swarm of gram-sized probes past Alpha Centauri at a fifth of light speed, to gather a few hours of precious data and beam it home. Any realistic first mission to another star looks like this: a small, fast, unmanned scout sent to look and to report, not to stay. The machine goes first because the machine can go, while the human, for all the reasons we have traced, cannot yet and may not for a very long time, and there is a real chance that machines will not merely go first, but go instead. As our robots grow more capable, more able to explore and study and even build on their own, the case for sending fragile, short-lived humans across such a gulf grows weaker. It may be that the exploration of other stars, and perhaps of the whole galaxy, belongs to our machines rather than to our bodies. We might come to know Alpha Centauri intimately, its planets mapped, its surfaces photographed, its air measured, all through the eyes of small probes, without a single human being ever making the crossing. The flag on the distant shore might be a robot's planted on our behalf. There is a gentler way to see this, though. Even a machine we send is, in a real sense, us. The voyagers carry their golden records, our sounds and images and greetings, a piece of humanity flung outward. A probe that reaches Alpha Centauri would carry our questions, our curiosity, our reach, even if it carries no living cell. When it sends its pictures home across 4 years of dark, it is human eyes, at last, that see them. In that sense we would have gone, through the machines that are our hands extended into the deep. But suppose that one day, machines having scouted the way, human beings did choose to make the crossing themselves, knowing all of it, knowing they could never return. It is worth facing, plainly and without flinching, what that choice would truly mean. Let us set aside the machines now, and the arithmetic, and imagine the human choice at the centre of all this, faced honestly and without flinching. Suppose that one day, everything we have described becomes possible. The ship can be built, the crew can be kept alive, a world worth settling waits at the far end, and a group of human beings stands ready to go, knowing, with complete clarity that they will never come back. What would it truly mean to walk through that door? It would mean the most total goodbye a person can say. Not the goodbye of a long trip, softened by the promise of a return, or even the goodbye of a dangerous mission shadowed by the hope of one. It would be a goodbye with no hope of return built into it at all, a leaving as final as death in its permanence, though the traveller goes on living. Everyone they ever knew who does not come with them, they will never see again, never speak with in any real way again, never touch or sit beside again. The whole world that made them, every place and face and familiar thing, would fall behind them forever the moment the engines lit. And yet, it would not be death. That is the strange and profound heart of it. The travellers would go on living and building and loving and raising children on the far side of that final door. They would simply do it somewhere utterly beyond return, in a new place, under a different sun, cut off from everything before. It is less like dying than like being born into a second life, one that keeps no thread back to the first except memory. They would carry Earth with them only in what they remember, and in what they choose to pass on to children who will never see it. This is why a one-way journey to the stars is not merely a technical problem, to be solved with better engines and stronger shielding. It is a human one, maybe the most human one there is. It asks whether a person could accept such a leaving and find it worth the cost. Whether the pull of the new shore could ever be strong enough to outweigh everything left behind. For some, surely the answer would be no, and that is no failure of courage, only a fair measure of how much home is worth. But for others, perhaps, the answer would be yes, the same yes their distant ancestors gave when they pushed a canoe into open water, or crossed a sea toward a land they could not yet see. Because in the end, the one-way door is not new to us. We have been walking through smaller versions of it for as long as we have existed. Every migration into unknown country, every final crossing to a distant shore, was a rehearsal for this, the largest leaving of all. The distance to Alpha Centauri is greater than any our ancestors faced, by a factor beyond counting. But the shape of the choice is the same one humans have made again and again. To leave the known behind for good, and to trust that a life can be made on the far side of the dark. And so we come back, as we always must, to where we began. To that single point of light, low in the southern sky, waiting patiently for anyone who looks up and wonders. Go back outside, on that clear night in the southern half of the world, and find it once more. Low over the horizon, in the constellation of Centaurus, that steady bright point of light. It looks exactly as it did when we began, a single warm star among the others, easy to miss, easy to walk past. Nothing about it has changed. Everything about how you see it has. You know now that it is not one star but three, bound together by gravity into a single family. Alpha Centauri, A. So like our own sun, you could hardly tell them apart. Alpha Centauri B, its smaller orange companion, the two of them circling each other on a patient 80-year track, and Proxima Centauri, the faint red ember drifting far out on the edge, too dim for any eye to catch, yet closer to us than any other star there is. You know that a world turns around that faint red star, a planet called Proxima b, roughly the size of our own, sitting in the narrow band where water might just be able to pool. You know the light reaching your eye tonight left that place more than 4 years ago, and crossed the empty dark the whole way to find you, and you know, now, what it would truly take to go. You have followed the arithmetic all the way down, the rocket that drowns in its own fuel, the bombs and the fusion fire and the sails of light, each a bold answer that still falls short, the dust that turns deadly at 1/5 of light speed, and the radiation that ages the body, and the terrible difficulty of ever slowing down, the clocks that drift out of step, and the home that will not wait, and the conversation stretched so thin across the years that it stops being a conversation at all. And underneath it all, the plain, quiet fact this whole journey has circled, Whoever crosses that gulf and reaches Alpha Centauri will almost certainly never come home again. Not for lack of courage or care, but because the distance and the time and the arithmetic of the trip itself leave no room for a way back. It would be a one-way door, the largest leaving a human being has ever made, and yet somehow the oldest kind of leaving too, the same choice our ancestors made when they walked out of Africa, or pushed their canoes into the open Pacific, or crossed a sea toward a shore they could not see. To go for good, and to trust that a life could be built on the far side of the dark. Maybe no human ever will. Maybe the crossing will always belong to our machines, small and patient and tireless, carrying our questions to another sun while our bodies stay safely home. Or maybe, someday, long after all of us, a few people will stand ready to go and will look up at that point of light one last time and choose it anyway. Either way, it is still there tonight, waiting, as it has waited through all of human history. The nearest shore across the dark, close enough to see with your own eyes, far enough to change forever anyone who tries to reach it. A single point of light, low in the southern sky. Look at it a moment longer before you go inside, and let the wonder settle gently into the quiet.